Hello, everyone. So today we're going to be extending what we already know about wave functions and expanding it to a little bit more of a complex nature as we're going to include some imaginary numbers. So one of the big things that we need to keep in mind is that a wave function doesn't actually need to exist solely in terms of real numbers. So it's actually possible to have an imaginary component, but we still have to satisfy those same four constraints that we had previously. The two big ones that we want to focus on is first, we want to make sure that our wave function satisfies the Schrodinger equation. Because if it satisfies the Schrodinger equation, this means that it's also going to have all those four conditions for the Schrodinger equation. It's going to be continuous, should be non-infinite, and should produce real results. So let's go ahead and try and apply the Schrodinger equation to a wave function with an imaginary component. So one classic possibility is just taking our old sine kx wave function, and now we're just going to make it imaginary, throw an I in front of it. So let's go ahead and try and apply our kinetic energy Hamiltonian to this expression. So when we do this, we're going to be having to take the second derivative of our wave function. Well, in this case, our I just pops right out in front of the derivative. And otherwise, we have the same process. The second derivative of sine kx is just going to be negative k squared sine kx. So in this case, all that's happened is I've added an extra I that shows up on the left, but also shows up on the right. So it turns out it isn't actually going to affect my energy at all. So throwing an imaginary number gives me the same energy as not including the imaginary number, at least when we're dealing with sine. This won't always be the truth, but it's true often enough. However, we have another key condition we also need to satisfy. We also want to always make sure that our wave function generates a real positive probability density. So this means that our probability density should always be positive. There's no way I can have a negative probability density, and if it's imaginary, it's also still right out. So let's go ahead and go back to our probability density. Our probability density is essentially the square of our wave function, but it's a little bit more than that. So previously, we were able to treat it just as the square. In truth, what it is we're taking our wave function times its complex conjugate. Now, we really need to take a bit to figure out what the heck a complex conjugate is, and the answer is actually fairly straightforward. And it's simply that if I have a complex conjugate, anytime I have an I just turn it into a negative I. So thus, I sine kx has a complex conjugate of negative I sine kx. And one of the reasons why this is really important is because once I then multiply out this expression, what I have is negative I squared sine squared kx. But here's the big thing. Because the definition of I is square root of negative 1. So the square of I is just going to be negative 1. So then negative 1 times negative 1, I get a nice value of 1. So thus, the probability density for I sine kx is just going to be sine squared kx. Now, one of the big things we can notice is that there is no imaginary numbers present. So this is a real solution, no imagination. And second of all, because we have the square of the sine, it also means it's also going to produce a positive wave function, because whenever it would give sine kx gives a negative value, by taking the squared, we essentially guarantee its positive nature. That said, it is worth noting that this will still produce an oscillating wave function, which is very important because we do expect oscillating probability density for a real solution of the wave function. So we are actually getting all of the features that we would like. It just so happens that our wave function is imaginary. But again, this is why it's really important to remember that the wave function is just a mathematical convenience, and it doesn't represent any measurable phenomena. The energy is measurable. The probability density is measurable. The wave function is just going to be our oracle who tells us where we can get all of the rest of our information. However, we're now playing around with imaginary numbers, so we're going to need a couple of extra equations to help us out here. So one of the classic equations that we go to when trying to manage imaginary numbers is Euler's formula. So Euler's formula is a way to essentially try and relate imaginary exponential terms to trigonometric functions. So what we do is we start with the exponential of ix. So the exponential of an imaginary number times x. Well, it turns out that this gives us a value of cosine x plus I sine x. So it turns out we can generate using an imaginary exponential function, we can generate a pair of wave functions that are pair functions that oscillate in the real dimension and in the imaginary dimension. So using these imaginary exponentials, we can actually construct wave functions that are purely real or purely imaginary, or more often a combination of the two. Now, it is worth noting that it is kind of tricky to prove Euler's formula, but it has a lot of really great utility. Now, one of the best, most interesting consequences of Euler's formula is what's called Euler's identity. So it's really where we put in a value of pi for x. So then we have e to the I pi. But that means that our x's here and here also become pi. So we have cosine pi and I sine pi. Well, cosine pi is just the same as -1. And sine pi is 0. So what we have is -1 plus 0 gives us an answer of -1. So consequently, this means that e to the I pi equals -1. So this is one of those fun little oddities we'll make use of every once in a while, because it does mean if you have a -1 value, you can't actually substitute in Euler's identity. And again, it really, it's most famous because it encapsulates the 5 fundamental constants in mathematics: E, I, pi, the weirdness that is negative numbers, as well as the unity value, 1. So all of those get encapsulated in terms of Euler's identity. So one of the reasons why we're going to spend a lot of time with Euler's formula, and to a lesser extent Euler's identity, is because it turns out that we've identified 3 potential solutions for a wave function due to the constraint that we need something that returns itself when we apply a second derivative. And those possible functions were sine, cosine, and exponentials. Well, ta-da, exponential, cosine, sine. They're all here. And it turns out that this is going to give us a way to relate these 3 functions, both in real and imaginary space. So there's a lot of utility. So one of the other things that's worth noting is we can take Euler's identity for a positive exponential, but it's worth noting that we also are going to have to deal with the complex conjugate of this exponential fairly frequently. So what we can then do is put in a negative value out front. So if I have a negative e to the negative ikx, well, what ends up happening is you can almost treat this like it's a negative I. So cosine x remains unchanged, but now my positive I becomes a negative I. And one of the ways to look at this is just like e to the ix has a complex conjugate of e to the negative ix, cosine x plus I sine x has a complex conjugate of cosine x negative I sine x. And so we're going to be using both of these formulas fairly regularly. as we're going to need to do a fair number of substitutions when working with our wave functions. However, another very useful feature is that sometimes I might not want to go from an exponential to the wave to my trigonometric functions. Occasionally, I'm going to need to go the reverse. And one of the ways we can do this can actually be shown by starting with combining our two complex conjugates here, e to the ix plus e to the negative ix. So we can go ahead and then put in these two expressions. And then what we'll note is I sine x is going to cancel out with negative I sine x. And all that leaves us behind is 2 times cosine. So this means that twice cos x is just going to be the sum of these two imaginary components. This is more commonly expressed as cosine x is going to be equal to 1/2 the sum of these two exponentials. Now, this has a lot of power in the fact that we already established that cosine x is actually a pretty good solution for for the wave function of a free particle. And that means if this is a good solution for the wave function of a free particle, so it is essentially this combination of our exponentials. And we're going to do a fair number of manipulations along this lines. However, it is worth noting that we aren't just limited to cosine and sine as wave functions for a free particle. We can also go straight to the exponential of ikx, where again, k is the same thing it ever was, and we're now dealing with the imaginary number as well. So what we can then do is start by trying to determine the probability density for this wave function. So we'll take this wave function times its complex conjugate. Now, when we do this, we can then make use of our exponential rules, because I can go ahead and just add together the exponents. However, you'll notice that if I try and add these two exponents together, well, then turns out we get some entertainment because they just end up canceling out. Ikx minus negative ikx just gives me 0. So this means that for the probability density, I have an answer of e to the 0, which is the same thing as 1. Now, this seems a little bit weird, but what this really indicates is that the probability of finding a particle at any point in space is the same as finding a particle at any other point in space. Because remember, my probability density is proportional to the probability. And if everybody's probability density is the same, it means everybody's probability is the same. As again, we have no x dependence. So no matter where you are, I'm equally likely to find the particle anywhere. And this actually helps illustrate one of the cool features of using an imaginary wave function. Because when I used cosine or sine, I had a probability density that varied. But in truth, when I'm dealing with, say, a free particle, I often have no preference for the particle to be at any given position. Any given position is actually equally likely. But the way we can have essentially a wave function with this constant density is by making use of our imaginary numbers, because they have these fun effects when I move into real space by taking a complex conjugate. However, it is worth noting that not only can we find our probability density, we can also use our Schrodinger equation to find the energy of this new wave function. So we can start by doing the hard part of this expression, which is taking the second derivative of our exponential, which essentially is just going to bring I squared times k squared down above and leaving the core portion of my function unchanged, as it should. However, remember, I squared is the same as -1. So this means that my second derivative gives me negative k squared e to the ikx. Then we can apply the rest of our Schrodinger equation and our Hamiltonian, which is negative h bar squared over 2m. So my negatives cancel, and then I end up with h bar squared, k squared over 2m, and then I just return back my original exponential. Then what we need to do is remember, because this is a Schrodinger in an operator form, we should have returned back our wave function, which indeed we did, and that everything else is the energy. So this means that the energy for this wave function is going to be h bar squared times k squared over twice the mass of the particle. Now, hopefully this should look fairly familiar, because it turns out this is the same energy as for our wave function of I sine kx, which is the same energy as our wave function sine kx, which is the same energy as cosine kx and I cosine kx. So all five of these wave functions have the same identical energy, but it is worth noting that each one has slightly different probability densities. And this is something that is worth acknowledging as we move into further into our quantum mechanics, is that it's possible to have many different wave functions that all have the same energy. But we're going to need to focus a little bit more on probability densities. And most importantly, we need a way to move from probability densities, which again are proportional to the probability, to actually finding a way to talk about the probability itself. That will be next time. Until then, take care.